Hi guys, I'm Enrico.
Hi guys, I'm Giulio.
So we're here to guide you through this laboratory experiment. This is what you need. A Linux machine, a digital storage oscilloscope,
A signal generator and a Raspberry Pi 3 and a breadboard, of course.
As for the cables and other external components, you need an attenuating probe, some BNC cables, and what is that?
A crocodile tape to BNC cable and a T-probe.
And of course,
The power supply for
micro
the
USB power supply.
for the Raspberry Pi 3.
Okay, so here's what you need to get started.
Okay, so here is the part where I comment the software we used for making this whole thing work. This is a makefile. So we use the ARM-non-EABI toolchain, and with these parameters, this is vectors.s, which is the bulk of the assembly code really. So we have the entry point, then the reset handler here. Hang is just a macro that's defined below. Then we have our Q handler, which I'll talk about in a minute. Then some constants. Here's the reset function. This is the part that moves to hypervisor mode. This dumps all the registers, and this part can get you to different other modes, but we're not using them, so we just commented it. Be careful that this file passes both through the assembler and the C compiler, so you have to comment it twice like that. And then at the end of this part, you just branch to not main. Not main is defined in the C file, so I'll talk about that in a minute. This is the hang part. This is two functions that we use in the C code. This is the other function. This is another function that we use in the C code, just enables RQ. And this is the RQ service routine. So we have lots of comments here, so you can refer to them. And basically you just have a toggle, which is actuated by a clear and a set macro. And since we have a timer interrupt as well to act as some kind of disturbance, of course you can turn that off. And we have a GPIO interrupt and a timer interrupt, and you have to go through both of them at each interrupt trigger. And at the end you just restore all the registers and you go back to your program. Then you have the C file, which is just a lot of constants. Here you refer back to the two assembly functions I talked about earlier. Here you enable the RQ. Here's a lot of defines. You can look in the datasheet. We use the same values here. The name here as in the datasheet, so you can just search for them to see what they do if this comment's not enough. And here's not main. This is called not main because some preprocessors may do some funky business with the functions called main, so be careful not to call your main main. It's very simple. You just set up the two pin outs and the in, and you just set the ARM timer. Here's plenty of comments on that. You enable interrupts, and then you stay here in this while true forever. And this small file is just a division of the memory according to a schematic we found online. And that's pretty much it.
So first thing, you have to switch on the signal generator here. Okay. Let's say for a frequency, for a square wave, having frequency start from something like 200 kilohertz. Then we need a square wave. Okay, so you set the square wave. Then you set the amplitude of the square wave to 5 volt peak to peak. and then you set the offset to 2.5 volts, such that your square wave is running from 0 volt to 5 volts. Then you use the T here, and you connect it to your breadboard using the cross-die clip. So pay attention. One, maybe the black one, is connected to ground. So here we have a ground, and this is the same. So this is a ground, and the signal should be an input to the pin number 6 in our project. Okay, so this is the input of our signal, and in order to see the same signal on the oscilloscope, you use the other termination of the T. Okay. Okay, and then the other terminal to the oscilloscope. Okay, and here you should see something right now. Then, in order to see the output of your circuit, you connect the probe to the second channel of the oscilloscope. Okay, here. And then it is connected to the pin number 16, and then the other terminal to ground as well. So here we have the common ground. Okay, so let's zoom in and see what happens to our circuit. Well, right now it is in persist infinite, so we switch it off. Okay. And we start. Right now what's happening is that you have basically an overshoot because the ground is not enabled, as the Raspberry Pi 3 is not switched on. So right now the Raspberry Pi 3 has a power supply, so you can see it is referenced to the common ground, and you can see the 5 volt peak to peak of the channel 1, which is the one in yellow, but it doesn't have any output, which corresponds to the blue line, because we haven't inserted the micro SD card. So basically what we're gonna do is that we are gonna switch off our Raspberry Pi 3. So we switch off, we remove the power supply, we insert the micro SD card, which contains the proper code, the one that Enrico has explained to you, and we power on the Raspberry here, and okay, and basically you're gonna see the output that is toggling a square wave that's corresponding to the rising edges. And then in order to see everything, you should set the persist in infinite mode.
The persist basically retains the previous waveforms onto the screen like that, so you can estimate the uncertainty, or better, the skew of each toggle better. So,
and basically you see that the delay from the rising edge to the toggling of our output signal is basically something like 2 division, which corresponds to roughly 2 microseconds plus or minus something. So it is kind of 2 microseconds plus or minus 500 nanoseconds, and that's all.
And that's what you want to get. So again, don't worry about. So this configuration is for uncertainty estimation. That is the plus minus Julius was mentioning before, and this fast switching between on and off is the fact that the code, as I explained before, is not always going from one state to the other, but instead is toggling each time. So the oscilloscope shows that jump there.
Up to 460 kilohertz. So let's do it. Okay, as the input signal.
So let me turn on persistence, like show.
and that's what you want to get. Let me move it a little bit so that it matches up with a division, so you can estimate the skew better. And as you can see, it's more or less one division. So the result of the measurement is roughly 2 microseconds plus minus 500 nanoseconds. So as a conclusion, we'd like to thank Professor Montocchio and the whole computer architectures course of Politecnico di Torino, academic year 17-18. And
if you have any further questions, feel free to contact us.
To comment down below. And for anything else, please like, share, and subscribe, and all that good stuff. And we'll see you
Enjoy.
next time.